Another process is called sublimation, and this is the transition from a solid directly to a gas without going through a liquid. If we look at a block of ice, the molecules in the ice do have kinetic energy. They are moving, but they're moving about a fixed point. They're vibrating. Some of them have higher energies than others. If you have a high energy molecule that's at the surface, it can break loose and get into the gas state. The substance hasn't melted, but we've had water molecules go into the gas state. That's called sublimation. So we find that solids also have vapor pressures. The vapor pressures are just very, very small. The opposite process is deposition, going from a gas to a solid without freezing first. So this process occurs inside the freezer in your kitchen. If you've got a bag of tater tots, right, there's moisture, there's water inside tater tots, and they're sitting inside this bag, and the surface water molecules, some of them will sublimate, and they'll go into the gas state, and then they're bouncing around inside the sealed plastic bag, and eventually they're going to deposit and form ice crystals somewhere. They're not going to go back into the tater tot. That would be too convenient. They're probably going to go somewhere else. And this is why when you open a bag of tater tots that's been sitting there for a while, you dump it out in the pan, there's all these ice crystals. Like, who puts ice crystals in a bag of tater tots? Don't they know that when you stick that on the pan, it all melts and everything gets soggy? That's not a good idea. They didn't put those in there. That moisture used to be in your tater tots, and you didn't get around to cooking them fast enough, and so sublimation and deposition occurred, and the water separates from your tater tots. It's going to be worse in an open container, because then the particles can actually just leave, right? So if you have ice cubes that get left in the freezer, maybe you've got a tray of them in the back that got forgotten, or you got some that got stuck up in the ice maker, and you check them out, and they're a lot smaller than the rest of the ice cubes. Who's making miniature ice cubes? Nobody. Those were full-size ice cubes, but they have gradually sublimated and moved to other parts of your freezer. So we see ice crystals grow inside airtight bags of frozen foods. Foods get freezer burn and become dehydrated. You get a steak in there that's been in there too long, you pull it out, and parts of it are just dry and nasty, right? What happened to it? Well, the water left, right? You can reduce that problem by using a deep freeze. The colder the temperature, the less sublimation occurs, or by sealing the food very tightly without any airspace. Then the water can't get away. The most obvious example of sublimation is dry ice. This is a piece of dry ice. Dry ice is solid carbon dioxide, and it sublimes at room temperature but doesn't melt. Regular ice, I guess you could call wet ice, because as it warms up, it melts, right, and gets things wet. Dry ice never melts, and so anything that it's with stays dry. Okay, so fusion. Fusion is a fancy word for melting. If we take that block of ice and we increase the temperature, the molecules begin to move faster, and when we get to the melting point, they now have enough thermal energy that they can start sliding around each other and become a liquid. We can draw a heating curve for this as well, and we find that if we say take a block of ice at minus 10 degrees and we add heat to it, the temperature goes up until we get to the melting point. And at the melting point, just like at the boiling point, we have this place where the temperature will not increase until all of the solid has melted. Once the liquid has melted, or once the solid has melted to become water, then as we heat it, the temperature can go up again. When you're at the melting point, if you add more heat and more heat and more heat, all you're going to do is make it melt faster. The temperature will not go up until all of it has melted. Any additional heat just goes into melting more rapidly. So melting and fusion are two words for the same thing, the solid to liquid transition. I used to have a hard time remembering what fusion was, so it helped me to think about melting chocolate chips. So if you imagine putting some chocolate chips in a saucepan and heating them on the stove, as they melt, the chocolate chips fuse together, right? That's melting. Freezing is the opposite. It's going from a liquid to a solid. Freezing and boiling are not opposites of each other. Freezing and melting are opposites. Condensation and evaporation are opposites. So melting is an endothermic process. This makes sense to us because if you want something to melt, like if you want to thaw out a steak, what do? You put heat into it, right? It's an endothermic process. How much heat does it take? Well, that's called the heat of fusion. The heat required to melt 1 mole of the solid. So for water, at 6.02 kilojoules per mole. The opposite process, freezing, is exothermic, and that releases energy. That's not so obvious. We're coming into the winter season, and where I live in Reedley, we have a lot of citrus trees, and oranges are on the trees in the winter, and you don't want them to freeze because it just totally destroys them. But sometimes the temperature gets down cold enough to freeze the oranges, so what's a farmer to do? Well, you can't put a space heater in the orchard because it's just not practical. But what you can do is you can flood the field, put lots and lots of water out there. Because what happens then is as the temperature goes down and the water begins to freeze, it stays at 0 degrees until all of it's frozen. Because if we look at this heating curve, when we're going this way, the temperature won't go up until it's all melted. But coming the other way, it's also true. As we get it colder and colder, it begins to freeze, and the temperature will not drop until it has all frozen, and then the temperature can drop. So the process of water freezing on the ground of the orchard will keep the oranges warm. And then you throw some wind machines in there to blow the air around, and you can keep the oranges from freezing most of the time. Any questions about that? This bar graph is showing the heat of fusion versus the heat of vaporization. It takes a lot more energy to vaporize something than it does to melt it. Because melting, you only have to partially overcome the forces, whereas evaporation, you have to completely break all of the intermolecular forces. And then here's some heats of fusion for several different substances. These are not numbers that you memorize, these are things that you look up.